Restriction endonucleases, or more simply, restriction enzymes, cut DNA at specific sequences, unlike regular digestive enzymes. And because they will cut the same piece of DNA at the same sites, producing the same fragments, therefore are useful in applications in biotechnology. So here, for example, they can be used to map, say, a plasmid or any piece of DNA, but a plasmid in this case. And so that we could determine the sizes of different pieces relative to the sites where different restriction enzymes cut. Why would one want to do this? Well, given, for example, that you could, say, add a gene to a plasmid and move a gene from one organism to another, this might actually confer a new ability on the second organism that might be worth a great deal of money with, a transgenic line of bacteria which is useful for industry or is producing something that a hospital needs, etc. Let's imagine we run a gel where different lanes have different samples with differing numbers of fragments. And in the first lane, notice that a standard has been run. So we purchased this. We purchased a sample which would provide us DNA fragments of known sizes. So it is known that we should have a size fragment with 50,000 base pairs, 20,000 base pairs, 10,000, 3,000, 1,500, and 300 base pairs. This was provided in the information when we purchased this sample that we ran in the first lane. As a result, we can now bring in, say, a centimeter ruler and measure how far each of these fragments traveled in the gel. The bigger pieces move more slowly, so they have migrated farther from the origin. As a result, we now have information both on the size of the fragments and the distance traveled. As a result, we can now create a graph. We use semilog paper, where one scale on one axis has a logarithmic scale, just so that we'll get a straight line as a relationship rather than a curve. And given that we now have information for the x-axis, the distance traveled in the gel in centimeters, and information for the y-axis in the size of the fragments, we can then plot points. These points give us a line which represents the relationship between the size of a DNA fragment and the distance it travels in this gel. As I review in other videos, you can simply look at a gel and already get an idea of where restriction enzymes make cuts. So for example, if you run a lane with the sample which is uncut, let's say it's a plasmid, it's a circular plasmid, you'll get one band. It should be large in size because it's all of the DNA of that plasmid. If you add a restriction enzyme and then get two pieces, well, that then means that that restriction enzyme makes two cuts. The only way you can turn a circular piece of DNA into two separate pieces is to make two cuts. If you then add additional restriction enzymes and get three cuts, or forming three pieces, or four cuts forming four pieces, you now have an idea of the fragments that you have to map. And then you can simply bring that centimeter ruler again and measure how far each of the fragments traveled from the well where the DNA was added originally. Now, you want to know the size of these fragments, but given that line that you created showing the relationship between size of a fragment and distance traveled, you can now identify these fragments that are unknown simply because now you know how far they've traveled. And so you can go to your graph paper and say a fragment which has traveled 2 centimeters or 4 centimeters. If I then drag this up to where it intersects the line, I can then carry it over to the y-axis and get an estimate of the size of that piece of DNA. And that's all you need. The gel has provided the number of fragments from each lane after adding specific restriction enzymes. You can measure the distance that a fragment travels from the well, and then using this graph, you can see the correlation between distance traveled and size. And once you know the size of the fragments, you can then reconstruct the restriction sites on that plasmid, as is described in a bit more detail in the videos depicted here when played in their entirety.